now, non funzionava. Ok. Ok? No. Okay. Now we have YRM. She will speak about the study of the eclipse region in the red-back millisecond pulsar, J14, 31, 47, 15, okay. Now we have YRM. She will speak about the study of the eclipse region in the red-back millisecond pulsar, J14, 31, 47, 15, okay.
Good morning, I'm YRM. I'm a master's student at the University of Padova, and I'm doing my thesis work here at the Observatory of Cagliari with the supervisors Piquet and Possenti. Today I'm going to talk about the study of the eclipse region of the red-back millisecond pulsar J14, 31, 15. I'm doing my thesis work here. In the first part of my presentation, I will make a brief introduction on pulsar and the emission model. I will talk about two classes of pulsar, the normal one and the second one. And I will focus on a subpopulation first part millisecond pulsar that are the eclipsing binary millisecond pulsar, and in the second part of this presentation I will talk about our analysis showing results obtained and future perspective of this thesis work. The first pulsar was discovered in 1967 by Joseph Bell and Professor Anthony Hewish. Pulsar are very small compact objects with radius about 10 kilometers and mass about 1.5 solar masses with very high average densities. Pulsars are highly magnetized and roughly speaking star. Their magnetic field is between 28 to 10 to the 12 Gauss, and their rotational period is of the order of seconds up to every second. Their progenitors are massive stars with masses between 10 to 25 solar masses that explode as a supernova. The emission model is explained with the lighthouse model, in which charged particles are accelerated along their progenitors, forming a beam, and if we lay in the path of the beam, we see the pulse every rotation. Assuming the most simple model, it assumes that the emission is due to the rotational energy loss in the form of magnetic dipolarization. We have the first formula in the box, where I, S is the moment of relation of the star, omega is the angular velocity model, the emission velocity, Bs is the magnetic field of rotational star, Rs is the radius, and alpha is the angle of radiation. We have in the box where I axis. If we assume alpha 19 degree and the moment of inertia and the radius of the star, we can derive the second and third equations that are magnetic field and the age of the pulsar that depends on the period and the derivative if we assume period. Here in the right plot we have the PP dot diagram with the spin period of the pulsar and the derivative of spin period. And if we assume this simple model, we can recognize two types of pulsar, the normal one and the millisecond one. The normal one, like pulsar that we can see in this combined image, occupy the central position of this diagram because they have high magnetic field and high derivative of the rotational period, and they are relatively young and mostly are single star, not in a binary systems. On the contrary, millisecond pulsar that have been recycled by accretion from an evolving binary companion stay in the bottom left in this diagram, and they have a weaker magnetic field and mostly are in a binary systems, and also are very old with ages 10 to the 9th years. Here we can see the formation of the neutron star. In the right plot we have the period magnetic field diagram with the spin evolution of the neutron star. There is a correspondence between this diagram and the left cartoon. At birth, a neutron star spins fast, but slows down in a relatively short time scale due to the rotational energy loss. And when the deadline is crossed, the pulsar switches off. But if the pulsar is in a binary system, in particular in a low and intermediate mass X-ray binaries, the neutron star accretes material and angular momentum, like we can see in the third image. And at the end of this phase, the pulsar spin up to become a millisecond pulsar, and the magnetic field of this neutron star decreases to 10 to the 7th, 10 to the 9th Gauss. Eclipsing binary millisecond pulsar are a subpopulation of millisecond pulsar, and in this system the millisecond pulsar very often show eclipses of the radio signal. In fact, the presence of a low dense ionized gas enwrapping the companion causes a delay in the arrival time of the pulse profile or an absorption of the pulse signal. We have two different systems that are black widows and redback systems, such name because the pulsar are updating the companion, and black widows have semi-degenerate companion with masses lower than 0.1 solar masses, and redback system have non-degenerate companion with masses between 0.1 to 0.4 solar masses. Recent observation of this system confirmed that these systems can swing between two different phases, an accretion stage in which the companion transfer material to the neutron star, and so systems are bright in X-ray, and the other phase is a rotational or quiescent phase, which the rate of mass transfer decreases and the pulsar turn on and emit from radio to gamma ray band. In our work, we analyzed data acquired with the Parkes radio telescope that, like Sardinia radio telescope, has a 64-meter diameter primary mirror. Our system was discovered in the high time resolution universe survey. We have observation acquired with 3 different backends from 2011 until today, at 3 different frequencies, 0.7, 1.4, and 3.1 gigahertz. Thanks to the discovery paper from Bates et al., we know that the period, the rotational period of this pulsar is about 2 milliseconds, and the system was classified as a redback system for the mass companion about 0.1 solar masses. In our analysis, we want to determine the time of arrival of the pulsar, and so first of all we extract one or more pulse profile for each observation by dispersing the signal due to the interstellar medium, and by folding the data in each band and each subintegration at the spin period of the source, and we extract the concentric time of arrival with a cross correlation between each pulse profile and the standard profile with high signal to noise. Here we can see 3 different standard profile at 3 different frequency. We notice that there is an evolution with the observing frequency. The first is 3.1 gigahertz, the second 1.4, and the third 0.7, and also have different signal to noise, these profiles, standard profile. The next step is to convert the supercentric time of arrival in the barycentric one using this formula that takes into account some correction, like the clock's correction chain, the dispersion of the radio pulse in the interstellar medium, Romer, Einstein, and Shapiro delay. Our aim is to count all the pulses arrived from a reference epoch and to predict the time of arrival of all next pulses. And so we model the rotational evolution of the neutron star with a Taylor expansion of the number of rotation. Here we have n is the number of rotation from a reference epoch. We have the frequency, the spin frequency, the first and second derivative of the spin frequency. With this model, we calculate timing residual. That is the difference between the observed time of arrivals and the value predicted by our model or by our pulsar ephemeris. In order to measure the best fitting for the astrometric rotational and orbital parameter, we minimize the weight K square, and we obtain this timing solution for our systems. That we have the start and end of timing data and the reference epoch in modified Julian day, the position and the proper motion of the source, the spin frequency and the first derivative of the spin frequency. We have also the dispersion measure, that is the integral of the number density of free electron along the line of path. The line of sight. We use the IL1 binary model because our system has very low eccentricity. We measured the orbital period, and the new parameter is the derivative of the orbital period because we have data span quite long to measure this parameter. We also measured epsilon 1, epsilon 2 that are the eccentricity for the system multiplied for a function of the longitude of the periastron and the epoch of the ascending node in the modified Julian day. To calculate this timing solution, we also calculate the timing residuals. In the left plot, we have observation at 1.4 gigahertz, excluding the observation during the eclipse phase, for the detection of the best fitting time parameters for the rotational, astrometric, and orbital parameters. These timing residual are randomly distributed around 0. And we have also modified Julian day versus post residual fit, and in the right plot we have frequency versus post residual fit with observation at 3 different frequencies for the detection of the dispersion measure. In fact, the delay due to the dispersion measure depends on the inverse square of the frequency. And in the second part of our work, we focus on the eclipse mechanisms. We assume that the responsible of the eclipse is a low-dense ionized Gauss cloud that enwrapping the companion, and the mechanism that that can account for this disappearance or decreases of the pulse signal are free absorption, Raman scattering, plasma frequency cutoff, that are absorption processes, and the last one is a dispersion measure smearing that causes a pulse smearing due to the rapid variation of the dispersion measure in the region of the eclipse, and also a delay in the time, and causes also a delay in the time of arrival. In our case, we think that the delay is due to an excess of dispersion measure, and here we can see the formula, the delay that depends on the variation of the dispersion measure, and is an integral along the cloud, so only the region of eclipse, and also depends on the inverse of frequency square. So here we can see the timing residual for all the data acquired over a time span of 5 years at 3 different frequencies. In particular, in green we have 1.4 gigahertz, in red 0.7, and in blue 3.1 gigahertz observation. In orbital we have orbital phase versus post-residual fit, and in the orbit between 0.1 to 0.4, we notice a delay in the pulse signal, but not a disappearing of the radio signal. The orbital period is about 10 hours for this system, and the duration of the eclipse is about 2 hours. We noticed that the delay depends on the observing frequency. In particular, 3.1 observation showing shorter delay than 0.1 gigahertz observation. In conclusion, with this work, we have obtained a timing solution that is in agreement with that of Bates et al., and we also calculate a new parameter, the derivative of the orbital period, thanks to a large time span of our dataset. We found a delay during the eclipse phase that covers about 20% of the orbit, and we found a pulse profile evolution with the observing frequency. Now, we are modeling different eclipse mechanisms, varying the system geometry, and at the end of this work, we want to compare theoretical results with experimental data, and future perspective of this work is to combine radio observation with optical and X-ray data in order to put some constraints on the system geometry, intra-binary shocks, and pulsar wind. Thanks.
Okay, thank you, Elena. There are questions? Okay.
Why are there more observations at 1.4 gigahertz than in other frequencies, other band?
Okay. In this plot, yes. We have the pulsar was mostly observed at 1.4 gigahertz because the signal to noise is higher than in the other frequency. For example, at 0.7 gigahertz, the signal was very noisy, and in many observations the pulsar was not visible but we plan to observe these systems at different frequencies in order to study the eclipse mechanisms.
Okay, other questions?
Have you measured any variation of time of passage through the ascending node?
No.
There wasn't any need of that?
No.
So one orbital period derivative was enough to obtain?
Yes,
okay.
enough to.
And what about the optical companion?
The optical companion, it's never observed, so we want to observe in the future, but...
Okay. Thank you.
What's the redback millisecond pulsar? What is it? Redback.
Redback, the name is a spider, okay. The Redback and Black Widow are particularly binary systems, and the peculiarity of this system is that shows an eclipse during their period, and the companion that in particular in Redbacks has non-degenerate. These systems have non-degenerate companion, and so this.
Okay. I think okay.
So, in conclusion, you said that you are simulating different geometries of the system. What do you mean?
Yes, the code that we use provide different geometry. Geometry for the companion and the gas that wrapping the companion star. In particular, we use sphere, ellipsoid, paraboloid, and cometary tail. And for each of these geometry, we can vary the density profile. In order to put some constraint on the eclipse mechanism and the system geometry with observation at different frequency.
Okay, so you are varying the geometry of the companion?
Yes.
Okay, thank you.
Okay, we have another question here.
First, thanks for being didactic. I really could follow your talk. My question is really basic, maybe too trivial. In one slide you show many physical quantities and then numbers on the other side. Is there a meaning of the numbers here? I mean, the error on these numbers, how do you compute it? And the decimals here?
Okay. Yes, for calculate this timing solution, that's we used a program in particular that is Tempo 2 for the detection of this, and the program used also a Taylor expansion for the detection of this parameter, and so for the error.
Okay. So it's a standard way to present this kind of data. Thanks.
Okay, thank you, Arianna. Next speaker is Sara Loro. She will talk on modeling spatially resolved spectral supernova remnants with the Sardinia Radio Telescope.
Good morning, everyone. My name is Sara Loro, and I'm a PhD student in University of Cagliari. I work to the Astronomical Observatory of Cagliari with my research group, Alberto Pellizzoni, Elisa Egron, Noemi Iacolina, and other collaborators. My research work is based on the study of two supernova remnants called W44 and IC443 in the radio band by using Sardinia Radio Telescope data. Using maps of these sources at different radio frequencies, we can perform a characterization of their spatially resolved radio spectra, and this is necessary to disentangle peculiar hadron contribution in the high energy spectra, and in this way better constrain supernova remnants as cosmic rays emitters. In this presentation, I will describe the supernova remnants W44 and IC443 and the main feature of their emission spectrum. So, I will describe how my research group and I performed the observation and the data analysis with the Sardinia Radio Telescope. And finally, I describe our results, in particular regarding the spectral index studies and our future prospects. Supernova remnants results from stellar explosion whose shock waves associated put a large fraction of their energy on magnetic field and accelerated radio-emitting electrons and gamma-ray emitting heavier particles with a substantial impact both on remnant dynamics and on the galactic population of cosmic ray particles. W44 and IC443 represent an ideal target for our studies thanks to their interesting and complex morphology and to their availability of extensive multi-wavelength data. W44 is a bright radio supernova remnants with an asymmetric morphology. And it belongs to the remnants mixed morphology class, characterized by an highly filamentary radio shell and central thermal X-ray emission. It represents a rare case because it interacts with its parent molecular clouds complex. IC443 is one of the best studied galactic supernova remnants. It presents a large structure and shows evidence of interaction with both atomic and molecular clouds. Supernova remnants exhibit spectra typically featured by synchrotron emission rising from relativistic emitting electrons in the radio band. And high energy emission from both leptonic processes like Bremsstrahlung and inverse Compton from radio electrons interacting with ambient photons and hadronic processes of pi-zero meson decay, which is a direct signature of cosmic rays emitters in the supernova remnants. Bremsstrahlung and inverse Compton bumps in the gamma ray band are bounded with the synchrotron spectral slope in the radio domain, and for this reason is crucial constrain the lepton contribution first with the radio observed parameters in order to disentangle the hadronic contribution in the high energy spectra, and in this way better constrain supernova remnants as cosmic rays emitters. It's clear that the interaction with the interstellar medium can influence the morphology of these large sources, and this is evident in interferometric images that thanks to their higher resolution can show amazing details in the supernova remnant structure, like the extreme filamentary and the clumpy emission structure, and that are related with different regions of interaction with atomic and molecular clouds. However, recent constraints on cosmic rays emitted in supernova remnants, accelerated in supernova remnants, and related models are based on the simplistic assumption of a single electron population for the whole supernova remnants. However, the interferometry present two main problems. In fact, interferometric images provide a lot of details in the supernova remnants morphology, but accurate flux measurements are hard to obtain. Secondly, synthesis imaging of large sources like supernova remnants are feasible with the interferometric techniques only for in low radio frequencies. Furthermore, to study possible spectral break in the radio band and to identify the structure within the supernova Raman where this break take place are necessary radio observation at high radio frequency, and only single dish telescope can do it. In this context, are very important the results obtained with the Sardinia radio telescope. In fact, we with the Sardinia radio telescope we obtain accurate images using the on-the-fly technique, and thanks to imaging performances of the Sardinia radio telescope, thanks to innovative and ad hoc imaging techniques based on the fly scans, we can obtain supernova remnants maps that provide details of the structure of these sources comparable with the interferometric images carried out with VLA at low frequencies. In the aim of studying the local properties of supernova remnants, we perform accurate on-the-fly scans of these sources at 3 different radio frequencies with the Sardinia radio telescope: L-band 1.5 GHz, C-band 7 GHz, and K-band 22 GHz. A first series of observation was performed during the astronomical validation of the Sardinia radio telescope. Then a large program dedicated to observation of supernova remnants was approved during the early science program of SRT. We perform, we carry out mapping of W44 and IC443 using the on-the-fly techniques. These techniques is based on the acquisition of data with continuity and constant speed. Repeatedly scanning the sky in 2 directions, typically right ascension and declination. We produce our data analysis by using the SRT single dish imager, a tool designed to perform single dish imaging and that we improve for the on-the-fly scans. In particular, you introduce innovative techniques for the radio frequencies interference, rejection, baseline subtraction, and calibration. Our first results are presented in the recent published Egron et al. Paper. In this work, in particular, we show the first images of W44 and IC443 at 7 GHz. So we perform, we test the performances of the Sardinia radio telescope during a 2 years long time span, and provide a self-consistent check in measurements performed with 2 different backends. We compare our images and with the interferometric data carried out with the VLA at low frequencies, and discussed physical implication of the region-dependent spectral indices observed in the spectral index maps that we obtain coupling L-band and C-band maps. In this slide I show the images obtained with SRT of W44 and IC443 at 1.5 and 70 GHz and related integrated flux measurements. We can see in this slide that our images, both for W44 and IC443, show detailed structure of these remnants comparable with the interferometric images obtained at low frequencies. But a very important result is related with the integrated spectral indices observed. In fact, our results obtained are in agreement with the results with the integrated spectral index obtained at low frequencies in the previous studies. But regarding the integrated spectral index obtained at low frequencies, we can see that there is evidence of a spectral steepening at high frequencies, about 1 GHz. However, gamma ray observation show steepening of the primary particle spectrum at about 10 GeV for W44 and 100 GeV for IC443. Related to a synchrotron spectral slope at about 10 GHz and not 1 GHz as show our results. So how can we explain our results? One solution could be related to secondary electrons produced by hadronic interaction. Recent theories show that these secondary electrons take to 10% of the primary particle's energy, and in this case spectral index, synchrotron spectral index break at about 1 GHz is expected, and our observation at 22 GHz, so at high radio frequencies, are very useful for discuss at this point. We perform observation of W44 and IC443 with the Sardinia radio telescope at 22 GHz using the K-band 7-feed receiver shown in this slide, using the best space coverage configuration in order to cover the whole area scant with 7 equally spaced on the fly scan, as shown in this schematic illustration. We use the supernova remnant 3C10 to test our data analysis tool, and in particular in regarding the calibration. We implement an algorithm to merge the maps related to each single feed, and this way we obtained final maps characterized by about 14 scans per beam, and this is very important to optimize the final image accuracy. We perform the same data analysis on the K-band data of W44 and use related integrated flux measurement with the measurements obtained 1.5 and 7 GHz in order to study the integrated radio continuum spectrum of these sources. And our preliminary results show a spectral break between 7 and 22 GHz, and this is in agreement with a steepening of the primary particles spectra at about 10 GeV as suggested by gamma ray observations. But in the aim of studying the local properties of these large sources, we perform spectral index maps coupling L-band and C-band maps. And this slide I show the spectral index map of W44. And in this way, in this other slide, show the spectral index map obtained for IC443. Comparing the spectral index map, in this case of W44, and the C-band maps, we can see that there is a flat spectrum from the bright regions located at the supernova remnant limbs, while steeper spectral indices are observed in the fainter central regions and halos. Spectral index scatter along the supernova remnants show that the assumption of a single electron population is too simplistic. We are assessing different origin of spectral index scatter observed, like non-uniform absorption processes, secondary electron production, region-dependent cooling rates, and intrinsic shock parameters differences. But our aim for the future is to perform the same data analysis shown here for W44 on the supernova remnants IC440 in order to look for possible spectral steepening as observed for W44, and furthermore coupling K-band maps and C-band maps, we will obtain very accurate spectral index maps in order to search possible spectral index steepening in selected supernova remnants regions. Thank you.
Thank you, Sarah. There are questions? Ok. Marco. No, qua. Here.
In K-band, for the imaging of W44,
yes,
I seen a white dot. What is this? White dot in imaging of
white.
The other source, not the W44.
Ah, sorry.
This is a white dot. Yes, yes. What is this?
Is a good point. Science, maybe we think that could be the pulsar with nebula. That is that we can't observe in other low frequencies. In L-band and C-band we can't observe it, but in K-band maybe this is will possible. This will could be possible, but is our future prospect to study it.
Okay, other questions?
What kind of software you use to analyze those maps?
We use SDI software developed with IDL.
Okay, because in biology there is more or less the same problem to analyze some maps of different colors and different color changing through the maps, and this software can actually spot places where the value of the matrix has a drop or increase, right?
Okay.
Is that what is doing the software, more or less?
Yes, we use DS9, the software called DS9 for the image production and the measurements of flux density.
Okay, thanks.
Okay. Other questions? Okay, so thank you, Sara.
Thank you.
Now we have Alessandro Buzzelli speaking on the impact of the polarized foreground on LSPE swipe observations. Okay. Okay. Control.
The topic of my talk is about cosmology, that is the branch of astrophysics interested in the evolution, in the content, and in the first stages of the universe. The most important tool to extract cosmological information is the so-called cosmic microwave background, that is the oldest light in the universe, and someone has called it the echo of the Big Bang. And the microwave background has been observed for the first time only in 1964. And in particular, the microwave background could constrain the existence of primordial gravitational waves. And the main obstacle to observe the imprint of primordial gravitational waves in the microwave background is the presence of galactic contamination, the so-called foreground contamination. And many experiments have been planned to observe the microwave background with increasing accuracy. And here I focus on the forthcoming LSP swipe experiment. And I will show some forecast on the impact of this foreground contamination on LSP swipe observation and the effect that this contamination can have on the main goal of LSP swipe, that is to observe for the first time the imprint of primordial gravitational waves in the microwave background. So I will start with a short introduction on the microwave background, and I will introduce the LSP swipe experiment, and I will show my forecast on the effect of this contamination on the LSP swipe experiment. The microwave background is the oldest light in the universe, and it is freely streaming since around 400,000 years after the Big Bang. And it is the most perfect black body ever observed, and it has a temperature of around 2.7 Kelvin, and it is extremely isotropic, with a small fluctuation of only few parts out of 100,000. So we have the so-called hot and cold spots. And we can write this fluctuation as delta T, where T is the average temperature, and so we can expand the fluctuation pattern in terms of spherical harmonics, where A and M are the expansion coefficients. The microwave background is characterized not only by intensity pattern, but also by a pattern in polarization that can be described by a simple tensor of rank 2, PAB, which is symmetric and trace-free. And here Q and U are the Stokes parameters, and M is the vector theta phi of the direction in the sky. And as we expanded the intensity pattern in spherical harmonics, we can do the same here with the pattern in polarization. And here the expansion leads to two components, the so-called E and B components. So the microwave background can be analyzed with a quantity describing a temperature, and two quantities, E and B, describing the pattern in polarization. In particular, the E component has been widely observed, and it comes from both scalar and tensor primordial perturbation. Scalar perturbation are simply the seeds from which cosmic structure, like galaxies and cluster of galaxies, comes from, and the tensor perturbation corresponds instead to the primordial gravitational waves. And instead, the B component has not been observed yet, and it comes from only tensor perturbation. That's why an observation of the B component of the microwave background could constrain the existence of primordial gravitational waves. And starting from the expansion coefficients, we can introduce the so-called angular power spectrum, CL, that expresses the amplitude of the fluctuations as function of the multiples L, that are inversely proportional to the angular scale of the fluctuation. And so low multiples correspond to big angular scale. And in total, we have 6 spectra. The autospectra, CL, TT, EE, and BB, and the cross spectra from the combinations, TE, TB, and EB. And theory predicts that the cross spectra TB and EB are 0, so we are left with 4 spectra. And the only spectrum to be still observed is the BB1. Here we have the TT, TE, and EE power spectra as observed by the Planck mission. And Planck is a space experiment launched around 8 years ago, and it has provided so far the most accurate observation of the microwave background. And this spectra contain a lot of cosmological information. As I already said, the observation of the B component in the microwave background is the new frontier of observational cosmology, since this component can confirm the existence of a primordial gravitational wave background. And the primordial gravitational waves have an amplitude much lower than the waves from compact astrophysical objects. So the only way we have to observe it is in the microwave background. And the amplitude of the BB spectrum can be given in terms of the R parameter that expresses the amplitude of tensor perturbation with respect to the level of scalar perturbation. And the current upper limit is slightly less 0.1, while the theory predicts a value greater than 0.001. And here we have some BB spectra from theory for different values of the R parameter. Here the spectrum that corresponds to the current upper limit, and here the spectrum corresponding to the lower limit expected by theory. So we have still 2 orders of magnitude to investigate. And for comparison, we have in blue the TT spectrum, and in red the EE spectrum, while in green we have the effect of gravitational lensing that is due to the bending of the microwave photons interpret to us because of the gravitational effects of cosmic structure like a cluster of galaxies. And we can see that the BB spectrum has an amplitude much lower than the other spectra, and we can see also that the BB spectrum is characterized by a first bump at being angular scale that is due to the injection of energy during the first star formation, and the second bump that is the imprint of the primordial gravitational waves. The B component of the microwave background has a very low amplitude, so it's very important to distinguish it from other components. The main contaminants come from our galaxy. In particular, we have thermal dust emission at high frequency and synchrotron emission at low frequency. And the dust consists mainly of silicates and carbon grains that absorb optical and ultraviolet light and re-emit in the far infrared. Instead, the synchrotron comes from the electrons that are accelerated in the magnetic field of our galaxy. and the B component of the microwave background has an amplitude lower than the 1% of the foreground level. So the extraction of the cosmic microwave background from the foreground is a critical point. At first order, the dust spectrum is a modified black body or gray body of the shape Ni to the beta d times b Ni, where Ni is the frequency, beta d is the dust spectral index, and b Ni is the Planck function. The synchrotron spectrum instead is a simple power law with spectral index beta s. And here we have the amplitude in polarization of thermal dust and synchrotron in galactic coordinates. And we can see that the most contaminated part is corresponds to the galactic plane. As example of the impact of foreground contamination on microwave background observation, we have the well-known BICEP 2 case. BICEP 2 is a ground experiment that observed the microwave sky at 150 gigahertz from the South Pole. And the BICEP 2 collaboration a few years ago claimed to have observed the B component in the microwave background corresponding to a value of R equal 0.2. But following a joint analysis with Planck has shown that the excess that they found is completely compatible with the presence of dust contamination. So the initial claim was proved to be wrong. Here I focus on LSP, that is a forthcoming experiment aimed at observing the big component in the microwave background at a big angular scale. And LSP consists of two experiments, STRIP, a ground instrument, and SWIPE, a suborbital instrument. And here I focus on SWIPE, that will be launched in less than 2 years from the North Pole, and it will operate for around 15 days at an altitude of around 40 kilometers. And the SWIPE will observe around 30% of the sky at a frequency of 140, 220, and 240 gigahertz. And here we have the patch of the sky that will be observed by SWIPE. In particular, SWIPE we lost two symmetric orthogonal focal planes, and this is a picture of the two focal planes of SWIPE. In order to forecast the impact of the foreground contamination on SWIPE observation, I used the foreground maps observed by Planck as templates. In particular, I used a map at very high frequency at 353 GHz as template for dust, and a map at very low frequency at 30 GHz as template for synchrotron. And the first step is to scale these maps to the frequency of interest for the SWIPE. Instead, the second step is to estimate the level of this contamination in the sky patch observed by SWIPE. And these are the Q-Stokes maps of dust in first row and synchrotron in second row for a frequency of 140, 220, and 240 gigahertz. So these maps have been obtained from Planck observations after scaling them in frequency. And as expected, we can see that the amplitude of dust increases if we go to higher frequency, and instead the opposite happens to synchrotron emission. A very important point is the choice of a proper galactic mask to mitigate foreground contamination. In particular, we have to find a compromise between the foreground mitigation and the useful sky fraction. Because if we mask the galactic plane, that is the most contaminated part, to match, we may also lose useful cosmological information. Here we have the patch of the sky in galactic coordinates observed by SWIPE, and here a galactic mask that cuts out the galactic plane used by Planck, and here another mask extended to cut out plus minus 30 degrees from the galactic plane. In particular, this first mask is optimized in intensity, and the second step is